The metal smelting industry is a major contributor to industrial wastewater discharge. Its wastewater is complex in composition, highly toxic, and difficult to treat, and can be mainly categorized as follows. First, heavy metal-containing wastewater, which is the most representative wastewater from the smelting industry. Heavy metal ions such as copper, lead, zinc, nickel, cadmium, chromium, arsenic, and mercury are dissolved in large quantities during processes such as leaching, electrolytic refining, pickling, and flue gas scrubbing. Second, cyanide-containing wastewater, mainly generated in gold extraction and the cyanide leaching processes of certain non-ferrous metals. Cyanide is highly toxic. Even extremely low concentrations can be fatal to humans and aquatic life, and it is even more difficult to remove after forming complexes with heavy metals. Third, acidic and alkaline wastewater. Hydrometallurgical processes and pickling processes generate large amounts of strongly acidic wastewater containing sulfuric acid and hydrochloric acid, with pH values as low as 1 to 2, while alkaline washing and neutralization processes generate alkaline wastewater. Direct discharge of either will severely disrupt the acid-base balance of water bodies. Fourthly, there is fluoride-containing wastewater, mainly originating from processes such as aluminum electrolysis and rare earth smelting. Fluoride ions are seriously harmful to bones and teeth and easily migrate and diffuse in the environment. In addition, there is mineral processing wastewater and tailings leachate, containing flotation reagents such as xanthate and black reagents, heavy metals, and a large amount of suspended solids. Flue gas scrubbing wastewater, containing sulfur dioxide, acidic substances converted from nitrogen oxides, and heavy metals, as well as oily wastewater and high-temperature cooling wastewater. The core principle for treating smelting wastewater is classified collection, differentiated treatment based on quality, and end-of-pipe control. For cyanide-containing wastewater, separate treatment must be prioritized. Alkaline chlorination is the traditional mainstream process, which involves adding sodium hypochlorite or liquid chlorine to oxidized cyanide into low-toxicity cyanate under alkaline conditions, which is then further oxidized into carbon dioxide and nitrogen. For wastewater containing heavy metals, chemical precipitation is the most basic and economical method, depending on the type of heavy metals and water quality conditions. Lime slurry neutralization precipitation, sodium sulfide precipitation, or sodium hydroxide precipitation can be selected. After precipitation, coagulation and sedimentation with flocculants such as polyacrylamide can significantly improve removal efficiency. For applications with extremely high emission standards, ion exchange resins or membrane separation technologies can be subsequently used for deep purification. For fluoride-containing wastewater, calcium salt precipitation is typically used, with the addition of lime slurry or calcium chloride to precipitate fluoride as calcium fluoride. To enhance the fluoride removal effect, aluminum or iron salts can be used for coagulation, reducing the effluent fluoride concentration to below 10 mg/L. The treatment of acidic and alkaline wastewater primarily relies on neutralization. Acidic wastewater can be neutralized by adding lime, carbide slag, or by using alkaline wastewater. Alkaline wastewater is neutralized using waste acid or sulfur dioxide from flue gas, achieving waste-to-waste treatment. For high salinity wastewater, such as chlorine-containing or sodium sulfate-containing wastewater from certain hydrometallurgical processes, conventional physico-chemical methods are ineffective, requiring evaporation crystallization processes. Through multi-effect evaporation or mechanical steam recompression technology, salts are precipitated in crystalline form, and the condensate is reused, achieving zero wastewater discharge and salt resource recovery.